So we've looked at a very important example, the real numbers. Now we look at a couple of more examples. The first is kind of abstract but important, and the next 12 will be sort of mixture. It will be abstract looking, but it has to do with concrete things we do in mathematics. So firstly, cofinite topology. This works for any set, just like discrete or indiscrete, but it's a more interesting topology than the cofinite topology. Namely, let's look at a collection of open sets. Well, it's the empty set and those subsets V, let's say in X, such that if I look at the complement, this is finite. Okay, so this is called a cofinite set. So cofinite topology is where the any open set is exactly either empty or its complement is finite. So, okay, so let's first of all dispose of the property 3, which is phi is in omega, and also x minus x is phi is finite. The empty set is finite, so which implies that x is in omega. So the first one was just added by the definition. Otherwise, we have it that it's naturally whole space is naturally cofinite. It's as cofinite as you can get. It's co-empty. Okay, so co here is complement, of course. Complement is finite. Okay, so now let's look at the series properties. Okay, so let me, now I don't have to spell it out again and again. We want to show this union of V alpha in omega. If V alpha is in omega for all alpha. Okay, so this is what we want to show. Okay, so how would we look at this? Well, there are a couple of cases. So one case is if all of these are empty. Okay, if V alpha is empty for all alpha. This includes including the empty collection. If there are no sets at all, or all the sets are empty, then union of alpha in A, V alpha, is the empty set, which is in omega by definition. Okay. Now, if V alpha 0 is non-empty. So the opposite case is when at least one alpha 0, you have a non-empty case where alpha 0 belongs to A. Then we claim that the union is cofinite. Well, that's because then if I look at x minus union of alpha in alpha of V alpha, this, remember, is the intersection in alpha A of x minus V alpha. Now the intersection of sets is contained in each one of them. So this is contained in x minus V alpha naught, okay, which is finite. Okay, so therefore this x minus union of alpha in A V alpha is finite, and therefore union alpha in A of V alpha is in omega. So the union, arbitrary union of sets in omega is in omega. Okay. Our next property we need is finite intersections. So suppose we have V1, Vn in omega. This implies, so this is the property we are trying to prove, that V1 intersection Vn, the intersection of all of them, is in omega. Again, you have to have two cases. This time, if some Vi is empty, then V1 intersection Vn is empty, and hence it's in omega. So again, we have to split cases, being either empty or not. Okay, I just try a slightly straighter omega. Okay, but on the other hand, if all Vi not 0, then what we know is that x minus Vi, set difference, x set difference Vi is finite for all I. Okay, yeah, it's a finite index set. Therefore, x minus if I take the set complement of V1 union Vn, this is going to be, I'm sorry, we want the set complement of the intersection, not the union. Intersection. Well, this is going to be x minus V1 union and so on, union x minus Vn. Okay, and each of these is finite. Everything in between, and also we have a finite union. So finite union of finite sets is finite. Okay, hence we see that V1 intersection Vn belongs to omega. Okay, so we had a natural split into two cases, and so this gives an interesting topology. We'll see why it's interesting as we go along. Okay, so by the way, a remark here is that if you're looking at polynomials in one variable of real numbers, then you can see that the set of their non-zero points where they're non-zero gives you exactly this topology. We'll come back to this at some point. That was just a comment in passing. But now here's a non-example. We've been looking at too many examples. I mean, we have been looking not so much at too many examples, but as only examples. So we have to see what can go wrong. So example is that suppose I take x as now natural numbers, and I take omega is the subset of n, and like instead of demanding it's cofinite, which seems extreme, why not just require it to be infinite? Okay, so then let V1 be the set of prime numbers. That's infinite, thanks to a classic result of Euclid. And V2 is even numbers. Well, this is in omega because it's an infinite. This is in omega because it's infinite. Now then the intersection of this pair, well, it's just 2. It does not belong to omega. Okay, of course one doesn't have to be fancy and take prime numbers. It's easy to construct infinite sets whose intersection is finite. But why not take a nice example? Natural enough thing. Okay, so the key point is you can't just take a random collection of sets because they're finite intersections. Pairwise intersections may not be in that set. Okay, so you can think about the other case. I will just call it an exercise. Yeah. Well, intersections of finite set is finite. Okay, how about omega equals, again contained in natural numbers, V is finite. How about this is finite? Here now intersections of finite sets are finite. So that at least does not go wrong. Okay, you can think about these. But there are typical things are not examples. If one sees only examples, one may get under the illusion that that is the generic case. Okay, and the final example in this session, we'll vary this a little bit and look at now a topology on X is n hat, which is natural numbers union infinity. I'm just adding one point. And infinity you think of as the limit. And let me say omega is the set of all V in n hat such that V is contained in natural numbers. Okay, or equivalently infinity, the point infinity does not belong to V. So it's actually natural numbers. So on natural numbers, any subset of natural numbers is open. Okay, so this is a discrete topology when you are considering only natural numbers. This will become precise when we define subspace topology. But also we'll allow sets V contained in n hat which are cofinite. N hat minus V is finite. Okay. So we allow sets which don't involve infinity, and we allow sets which involve infinity but they are cofinite. Okay, you could be in both of them. I mean, you could be cofinite and contained in natural numbers, so there's no contradiction there. Okay, and the proposition is omega is a topology. Okay, again, property 3 we'll just get rid of. So phi is actually contained in natural numbers, and n hat, the space itself, is cofinite. Yeah. So this will be quite similar. So n hat is cofinite. And now I'm going to just use the fact that intersections of cofinite sets, finite intersections of cofinite sets and arbitrary unions of cofinite sets are finite. Okay, now so suppose now we have V alpha in A. Suppose these are all open. I have to show the union is open. Okay, so we consider this case. So now we have two cases. If V alpha is, previously we had if they were all empty, but in fact if they are all contained in N for all alpha, then V alpha is going to be, then the union alpha in N of V alpha is contained in N. So open. How about the other case? Suppose not. Okay, if some V alpha 0 cofinite, then let me just say then union of alpha in N of V alpha contains V alpha 0, and so if a set is cofinite, okay, which implies that it's cofinite. So if a set is cofinite, then any bigger set is clearly cofinite, and a union always contains all of the sets. Okay, and now secondly, if I take finite intersections, so V1, Vn are all open, that is they all belong to omega, and so we are considering V1 intersection Vn open. So let's assume the hypothesis as before, and again there are two cases. If some Vi is contained in N hat N, now if any one Vi is contained in N, then V1 intersection Vn is contained in N. So open. And otherwise, if all Vi are cofinite, then the same argument as before tells you that V1 intersection Vn is cofinite. Now the cofinite topology itself is nice for constructing examples and so on, but often not meaningful. But you think of cofinite as all but finitely many, this topology that we are considering here is extremely meaningful. Okay, so let's just see here the motivation for constructing this. So motivation. So if I look at a function, okay, alpha from let's say n hat to, for example, real numbers is alpha n, n in n, and alpha infinity in R. So this is alpha n in R. So you can think of, okay, let me not make that crude. So alpha n, n in n, and each one of them is in R. Okay, so each one of these alphas is in R. Sequence of real numbers and a limit point at infinity. Okay, and so open sets. So each point, so we'll see these more precisely as I said, but you can see that each point in N is open. This will mean, as I mentioned with the discrete topology, continuity tells you absolutely nothing about the points in N. Everything is automatically continuous. Okay, because continuity says if I take nearby points, that is points which are close to N, the values are also close to the value at N. Okay, but now do you have open sets which contain nothing but N, a point itself, so its value is exactly equal to the value at that point. Okay, but on the other hand, these cluster at infinity. So being close to, what does continuity at infinity mean? Well, it says that essentially all points are close to infinity, but if you want to say close enough, you can exclude only finitely many. So I'll just put this in quotes because we'll see this precisely. So close to infinity means all but finitely many, or equivalently sufficiently large points. So in fact, we will see alpha continuous is equivalent to alpha n converges to alpha infinity as sequences. Okay, so in analysis we see convergence and we see continuity, and these two are very similar. And even in topology, it's convenient to talk about convergence. But I define topology as if it was the universal way to capture this kind of notion. Well, this is partly justified here. So convergence can be captured in terms of continuity if you put the correct topology in this. Okay. Incidentally, you can also put a metric for these. You can think of the point infinity as actually the point 0. You basically take the reciprocals of the natural numbers. So their nth point becomes 1 over n, and then infinity becomes 0, and you can look at the distances there for those who know metric spaces, and you will get this. You don't actually need abstract topological spaces for this, but this is a nice illustration of how convergence is included in continuity as well.